Demonstration on how to identify how far points are from the line of best fit. And so we can actually see our line of best fit for weekly Aboriginal income versus non-weekly Aboriginal income um, right here. And so we can clearly actually see that this point is the furthest away. So that is one way to identify. So all we want to talk about here is the effect that that point does have on the graph, and that's the point that's furthest away. What we can do is we can get something called residuals. And to do the residuals, what we create is a model column. So what we want to do is, instead of having the y values, which are the measured values, which are the weekly non-Aboriginal incomes, we actually use the model. And so we say equals 0.992 times the x value plus the y-intercept, 119.586. So that's what it should have been. That first point's a little bit higher than that. If we drag that down, copy and paste it all the way down, it'll get you all your values. Then we can make another column called the residuals. And what the residuals do is we actually see how above and below the measured values are from what the predicted values should have been using the model. And so this guy was only 4 above, but this last one is actually almost $57 above. And so those are our residuals. And then with the residuals, we can actually calculate, we can draw like a residual plot. And so we just need like some measure of the x value, but really what we care is the y values. So it doesn't really matter what you use for x. We could use the model values. It's just, you could use the year as well. It doesn't really matter. But if we hit insert chart, we can do a scatter plot. And so ideally what you'd want to see is this like straight line, line of best fit on these guys. And so these are the distances every point is from the line of best fit. And so 0 would be right on the line of best fit, and then this guy, you can see the 57 higher, that's actually the furthest away. And so that's our residual plot. The reason why we want to do that is because we can figure out, then we can put a value on how far away they are rather than just eyeballing it. And so you can see the one that's really the worst, or a couple that maybe don't fit the line very well. What you might want to do with that is actually see the effect that that had on the model. So that 1 year, what effect did that have on the model? And so if we go back, so that's the residual plot. So if we actually go back to the data, back to our original graph, we had a slope of 0.992 and an r squared of 0.788. If we take out this point at all altogether, so just delete that whole row, now you actually have a slope of 0.899, so slightly lower. The y-intercept is higher, and the r squared is 0.889. So you can see the effect that that individual point had on the line of best fit. You can see the residual plot now. The furthest one is the negative 33. You can even go further and say, okay, well, what if you take it, and we don't have a lot of data to play with, but if you took that guy out now, you could see, oh, you're getting a lot stronger, a slope of 0.982 and an r squared of 0.915 as the data. And so it's just kind of seeing, all right, so what happened if that year didn't happen, or if that year lied more along the line of best fit? What would the equation then look like?